There we go. All right. Can everybody see this crazy wheel diagram and maximally entangled Professor Wolfram?
Yes, yes, we can see it.
Okay. So this was the hero image from the project and everything. So basically, this wheel right here is the current definition of SI. Dugan has brought it to my attention that as of 2030, they're planning on redefining all of this in terms of the second. That makes a lot of sense because we got some really good clocks, and you want to have whatever your basis of the units are on the things you have the most confidence in. Because with the 2019 redefinition, like I didn't even know. I was working on some stuff and I was looking at some numbers, and I'm like, well, the data listed here is different than what's listed on Codata right now. I had no idea why. Minor investigation, I'm like, oh, they updated this the unit system or the definition of SI in 2019, and they were rolling it out. Hence why certain things were changed, and then you have additional measurements and everything where they're trying to provide the most precise based upon a number of measurements and everything for different constants of nature, which now, for the most part, our units are defined off of here. So basically, we can see here, we'll get into this a little bit further here. Basically, one of the other things that I basically just said out loud what was already defined within the Wolfram Physics Project schema, so to speak, was that they have this term here, this zeta. What the heck is a zeta? Well, it's defined within the physics project as elementary energy divided by elementary time, which we have a scaling factor that we're going to get into that's different than this. It's basically G, and it's basically whatever you have that as, you would be scaling Planck units, and that's how they go by it. But the thing is, if you have an elementary energy divided by elementary time, it's going to give you the maximum of power. So it doesn't really matter what that is. So that's why I have Stephen all entangled here and a double cover, so to speak, of some hypersurface here. Um, and there's some interesting little tidbits once we get into this here. But I mean, I could just read through all of this. It's note. This is a new version. The previous version that I know some of y'all had gone through before, some stuff was just wrong. And then when Dugan had messaged me, he actually inspired me to go back, look at these things, go make those corrections. And I actually did add in another section because I kind of feel like I missed the plot, so to speak. The whole main connection was literally sitting right in front of me, and I completely missed it until this past week. So thank you, Dugan.
You're welcome.
So, so basically, our bases in SI, we have 7 base units as of now. So the bases are the meter, which is a unit of length, the second, which is our unit of time, the kilogram, which is a unit of mass, the ampere, the unit of current, the Kelvin, the unit of temperature, the mole, it's the unit that's counting and everything. It is an amount. And the candela, which is luminous intensity, and actually still it has a little bit of a reference to some of the SI units because it does have time in there, but it's ultimately attempted to reconstruct what a human would see for a single candle, which seems kind of crazy. But then again, if you are selling candles and you want a certain luminous intensity, well, you want it to actually be advertised right. Or if you have one of those like 1 million candle power flashlights or something, that's kind of fun sometimes. Just don't look directly into it. Okay. So basically, it's a quick overview of the summary of basically we have a particular factor here, that G factor there, which is basically this little thing over here. If I'm mispronouncing that at all, please correct me. I believe it's capital G is pronounced. But basically, there's this particular factor that the original estimates we're done calculating the estimated age of the universe and using some logarithmic recursion factor and everything. Long story short is I attempted to do something. I was off by 17 orders of magnitude. Xerxes gave me a pro tip at lunch. And then after having my mid-project meeting with Steven, he assigned me homework. So then, while doing my homework, I'm going through and I'm reading over space and time like hypersurfaces and stuff, and we need to have some notion of flux through our hypergraphs here and everything. And I go back and look at the calculation that I had done at lunch after Xerxes gave me the idea, and I'm like, according to Wolfram Alpha, this dimension or interpretation is flux. I'm like, that's interesting. What if I took that seriously? So long story short is I went in, I basically just stripped the dimensions out, which seems like a very reckless thing to do, and then it seemed to replicate a lot of the initial physics project findings within approximately one order of magnitude, which I mean I wasn't expecting that. But again, this is a speculative connection, but we're going to kind of break it down. All right. How the heck did we get here? Okay. So again, as it says, story of units is extremely vast, detailed, and I'm not going over everything here. There's large amounts of history that we do not cover. I think it's worth covering. And if you haven't looked into this, some folks are like, we just have these random units. What's the meter? It's like growing up, I'm like, oh, it's a little more than a yard because my reference is an American here stateside. It's like we're still imperialists, so to speak. We still use the foot and everything like that because reasons. I don't know. But ultimately, as certain units here seem to be arbitrary, they seem to get a little less arbitrary over time, and there's some interesting connections we're going to go through here. So sometimes you'll hear the saying, you want the right tool for a job. Quick aside, I used to do maintenance. I'm not saying I'm a good maintenance guy, but I'm just saying I did used to do it. And you can use a screwdriver to screw something in. Now, that might be applicable if you're using something like, if you're doing like a lock set or something. You want to have very precise motion and everything. If you're trying to screw in some drywall into some studding, you're going to want a power drill because otherwise, good luck. So it's kind of like you can build a house with an old school hammer, nails, and saw, but if you have a table saw and I don't know, a nail gun, you're probably going to do it a lot faster with a lot less headaches. So that's kind of how I look at a lot of stuff within the Wolfram language. Could you do all this stuff out by hand and stuff? Sure, you could do that. But why wouldn't you leverage the computational tools we now have available? And that's basically the only way I was able to do any of this. So thank you, Team Wolfram. But basically, if you're talking about units, I'm just going to read this quick example. So if you require something like a recipe, some of us may have culinary skills, some of us may not. But I'm just going to read this because I think it was stated decently well. So perhaps one requires 2 cups of flour for a recipe. With a requisite flour available in a unit measuring cup, no big deal. You just fill it up, you put 2 cups in, you're good. Now, however, if one does not have the requisite cup, then one may default adding 32 tablespoons of flour because 1 cup equals 16 tablespoons times 2 cups. If one has neither a cup nor tablespoon but a teaspoon, one would have to add 96 teaspoons of flour because 1 cup is 48 teaspoons times 2 cups. If one is unfortunate not to have any standardized measure, so to speak, then the age-old method of eyeballing may be applied. Good luck with that. I'm not good at that. As somebody like myself with no culinary skill, this may often lead to disastrous results. But it is a simple single example of a simple measure of volume. This is something that we often may come across just to kind of get it in our heads. And when you're starting off with units, we literally had them based upon human characteristics. So you all may have heard of the unit per qubit, not the modern quantum computing kind, but literally the qubit was the length of your arm to your fingertip and everything. Now, over time that would change, but to an observer like us, it's probably going to do pretty well. And people for hundreds, probably thousands of years have literally, actually, it has been thousands of years, have used that as a basis of measure because if you're building a house and you have a reference. Oh, it's about 1 qubit. It's about half a qubit and stuff. If you're using rough elementary tools and everything, you can probably build a house, have a successful farm, and have a living. Fantastic. The issue you run into is, again, it's a human basis and we're all different. So since human beings come in all different shapes and sizes, my qubit's likely going to be different from your qubit and everything. So one of the big things that we came back down to was we needed some method of standardization. And there's some very interesting ways that they went about this. So you also have things from the imperial system like the hand and the foot. So the hand is often still used to measure the height of a horse. The foot is still basically one of our standard units of measure here in the States as well. One of the interesting things that you come across here is people realize that everyone's different. So some of our British friends apparently had the great notion of let's utilize a standard distribution. So I'll just read from this part. So early methods to account for such variation led to the British rod, based on a randomized collection of 16 different men's feet. Well, we may credit those utilizing the power of a standard distribution. The problem here is still plainly evident. What sample are we taking? Are these folks all from a similar lineage of large footed folks, so to speak, or vice versa? Because that's going to end up skewing your results. Because again, it's literally based upon a human style metric.
Yeah,
So
I was going to
most of the
ask about
standard.
that, if I may.
Yes,
So
please.
like the qubit, like it's from your elbow to your wrist, right? Or to elbow to tip of finger.
I believe it. I believe it's here. I believe it's the shoulder to the tip. Hold
Oh,
on,
it
let me
doesn't
just go
matter. It
back
said
here.
forearm, but in any case, whatever it is, it's like there's going to be a variation in the population of that length. And so, like if you have a short arm, you might think, okay, we'll have a shorter cubic than the average. So like you kind of account for that. Or if you're longer, then you say like, okay, well my cubit's probably longer than average, so like you can kind of account for that. I remember Veritasium doing an experiment asking like coming around with a jar of like marbles or something, right? And you guess the number of marbles in the jar, and you ask a bunch of people, and the average is pretty darn accurate to like the true number. So if you know, on average, people are good about knowing what the average is. Let's say,
Yeah,
and
no,
it's
I
interesting
think
that
that's
also that they had a standard measurement thing like pick 16 people at random. Uh, Hopefully 16 average people, quote unquote, and then like take the average of that, and that'll be pretty good for most purposes.
a lot of folks in the past. Like a lot of these folks are really smart people just because it's like they obviously saw that this was an issue and they tried different ways of accounting for it. Now it's much easier to account for it when we have modern technology and we're literally like remote viewing this presentation at near the speed of light across the earth. I mean that literally is like magic if you went back like a few hundred years. But this is where I like to invoke Arthur C. Clarke's any sufficiently advanced technology is indistinguishable from magic. Now, you may or may not believe that, but I think that might help put different things in perspective. Cool.